Good morning, everyone. Welcome to our virtual lecture. Today is May the 21st, and I would like to get started with or before we get started with our lecture, as you may have seen in your emails, quiz number 1 is available online under quizzes. Please pay attention to the due date, which is next week, Tuesday. Please take note of the due date for the quiz. If you have any question, please send me an email. Please send me an email if you encounter any technical problems so that I can help you within the earliest convenient time on my end. Without wasting my time, I just want to recap what we talked about last lecture on Tuesday. We finished chapter 1, dimensional analysis, section 1.7. We started chapter 2, atoms, molecules, and ions, and we went as far as section 2.5. You should read the relevant section. Make sure you read the section 2.1, 2.2, 2.3, and 2.4 on the development of or technology in the revolution of the atom, or how the atom was revolutionized, starting from John Dalton's atomic theory. You should be able to state the postulate, all right? You should know the contribution of J.J. Thomson, the plumb-bounding model of an atom, the contribution of Milkan, the Milkan oil experiment, Ernest Rutherford. We talked about Ernest Rutherford, what did he do? You should be able to distinguish who did what. Those scientists, sometimes you may be asked in an exam that who contributed this, who did what, all right? You should also read the 3 laws which led to the development of the periodic, the atom. That is the law of definite composition, the law of mass conservation, all right? We looked at the isotopes. We defined the isotopes and look at how to determine the subatomic particles. That is mass number equals to the number of protons plus the number of neutrons. Using that equation, given 2, you should find the third one, right? And we know from a neutral atom, for a neutral atom, the number of protons equals to the atomic number on the periodic table for all the elements. So you should be able to calculate subatomic particles. The last item we looked at was how to find the atomic weight or formula weight for an element. You should be able to use this equation. This is the last thing we looked at, atomic weight, all right? Atomic weight, we abbreviate that, is given by the summation of isotopic mass, all right, in AMU, all right. Always this one is in AMU times we call this isotopic abundance. That means the percent, all right, and change that to decimal notation. Change that to decimal notation. Somebody's asking a question here. Let me see. All right. Somebody's asking a question here. Is the quiz through analog or lockdown browser? It's through analog, all right, Anthony, through analog. Are we allowed to use the scratch paper for the quiz? Yes, Scott, you are allowed to use the 2 scratch papers, all right, 2 scratch papers. Queen's Cook, I don't know if you answered your question. Let me see if there was any question. Do we download? Yes, you need to download. You follow the direction. I may want to repost if you look at the announcement. Jennifer, the announcement I did post yesterday, walk you through on how to download the Chrome browser and install the Honalog. Yes, you need to do that. All right, and there is the periodic, not the periodic table, but the calculator on the Honalog, which you will also use, you know, to do simple calculation, such as the density or maybe for significant figures in calculation. So please plan to complete a quiz in one sitting, because you'll have you cannot save and come back again. You have to complete the quiz in one sitting. I think it's fair to, you know, give you extended time. You have you know, from yesterday, today, weekend, whatever, until next Tuesday to complete quiz number one. Can we use our own calculator? No, you can use the one on the Honalog. There is a one which comes with the app. I mean, the program Honalog has a calculator similar to what you have on your, you know, on your smartphone. You just tap calculator and it will give you a window. It's not about, you know, finding some crazy calculation, simple calculation, which you can use the Honalog calculator. Is the quiz timed? Yes, it is 1 hour. You have 60 minutes, all right? You have 60 minutes, and then you have 60 minutes to complete 25 multiple choice questions. All right, thank you. All right, let's move on to, I want to just go straight to, this is the last thing I looked at on my whiteboard, you know, the equation used to calculate the atomic weight of elements, such as this, we solved this last time. We used this equation you see on the whiteboard on how to find the atomic weight of an element in AMU, atomic mass unit. Let's dive into the periodic table. Periodic table, this is not something new to you. You know periodic table. It is a list of elements, all right? You will see in any chemistry text a table of elements listed from hydrogen, helium, from left to right according to increase in atomic number, the position on the periodic table, all right? Elements are listed. How did we end up with this periodic table, or how did we end up with this? There must have been a reason. I gave you last time how the term atom came into the picture, all right, because of the law of mass conservation, all those three principles we looked at. But how did we end up with the periodic table as well? It turns out that back in the day, there were a few elements, maybe 3 to start off with: silver, which is precious, gold, which is precious, and maybe copper. You can remember those 3, and then the element, number of elements known at that time rose to about 24 or 20. People could memorize. But beginning 1800s, there was a remarkable discovery of elements. About 64 or over 60 were discovered at the same time, and people were like, how do we really keep track of what is what, you know? There was, you know, a lot of information to which they could not, until somebody said, we need to organize this thing. And there are some people who are, you know, made some contribution towards the periodic table. Just like right now, we are in under pandemic situation. A lot of people are trying to find a vaccine. It's not only one person, a lot of people. So likewise, on the development of the periodic table, there are some people who tried, okay, Newland, the law of octave, organizing the periodic table according to increase in atomic number 8, the law of triads. And but the modern periodic table is attributed to Mendeleev. We will see later on. So periodic from the word period, that means after. A decade, after 10 years, all right, after every 4 years, we do the election, a period of 4 years. This time period means here, when elements on the periodic table are arranged according to increase in atomic number, there is a recurring chemical and physical properties, all right? When elements are arranged according to increase in atomic number, all right, there is a recurring pattern in chemical reactivity and physical properties. You know what atomic number is? Atomic number is the number above the chemical symbol on the periodic table. This is atomic number 6, all right? This is atomic number 6. On the periodic table, element number 6 is carbon. You'll see all other elements, maybe hydrogen on this side. Number 1, hydrogen, number 1 with atomic mass number, atomic mass 1.00794. You don't have to memorize all these numbers I'm giving you here. You don't have to memorize those. You will be given the periodic table on those atomic numbers. You should know how to read what those numbers means. This is an example of periodic table. All right, you have seen this P4, and what I want you to learn right now is the organization. There are a lot of information on this table right here. Some of them we will not even need. You know, it does not apply to our course, but as far as we are concerned, this is what I want you to know. Periods. There are 7 periods. We call these horizontal rows. On this one, let me just define what you see. What you see on, let me just take this out of my way so that I can have my whiteboard. And what you see is a periodic table organized according to what we call group. All right, these are vertical column. All right, vertical column is called a group, and horizontal, we call this group or family. All right, a vertical column is called a family or a group on the periodic chart, or here is the period. We call this period or series. These are horizontal rows on the periodic table. There are 7 periods on the periodic table. There are 7. 1, 2, 3, 4, 5, 6, 7. If you look at this one, the inner transition metals, 56, and then you come down here, 57. There is 88, and then you come to 89. So basically, these guys right here is lumped in right here. And if we do that, maybe it will be an expanded periodic table. But remember, there are 7 horizontal. We have here 7, and we have here 18 vertical columns, 18 vertical columns. If you look at the numbering, there are 2 ways, all right? We have the American convention, all right? American convention. Convention, this means the systematic way we use here in the US. We use Roman numeral such as 1 or 1A, all right, a number, or 2B, like that, a number and a Roman numeral and a letter stand for American, but just 1 all the way through 18. This is according to IUPAC, International Union of Pure and Applied Chemistry. They use this numbering system 1, 2, 3, all the way to 18 on this side. It means the same thing. So when you see 1A, 2A, 3B, all right, 3A all the way to 8A, we will talk about that momentarily, what those means are. So this is typical periodic table, horizontal rows and vertical columns. So if you look at each element on the periodic table, you should understand what the number stands for in each box. This is stand for, all right? This is stand for atomic number. That means the position on the periodic table. This is the chemical symbol and stand for potassium. And this is the atomic weight. And remember how we calculated atomic weight? The equation I gave you earlier on how to find. If you look at this equation right here, this is what they use. Somebody had to use the equation you see on the whiteboard to determine this atomic weight based on all existing isotopes of potassium in this case. Any other element also follows the same pattern in calculating atomic weight. So that's what it meant by those numbers and the chemical symbol. The symbol, atomic number, and below it is atomic mass. So I've explained what horizontal rows are. We call those periods or series. Sometimes we use these series instead of period. And then vertical columns are called families or groups. Families or groups. If you take note of a group, element in one group, in one column, they have similar chemical properties because of valence electron we're going to talk about later on. And I guess that's why we call families. You know, in a family, you may share last name. There's common similarity within a family, maybe last name. Likewise, for elements, they share similar chemical properties, reactivity. They react the same way. We will look in chapter 6, electron configuration, and you will see that group 1 have one valence electron. We're going to talk about that. But remember that element in one particular group react the same way. In particular, the main group. This is for main group or representative elements. Main group or representative element are the A groups. A groups like this are the main group. They have similar chemical reactivity. What do I mean by A? If you look at 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A, we call those main group elements, all right? We call main group element or representative element. They have predictable chemical reactivity. The B, the transition right here, 3B, 4B, their chemical reactivity do not, or they are not predictable. Rarely will you see in this course and even came to compounds, except we'll see few, but not a lot of information we will cover in this course pertains to the B groups. What we'll be dealing with are the main group or representative because their chemical reactivities are predictable. So remember the groups and the periods. Now, periodicity is a term used to mean that when elements are arranged according to increase in atomic number, you use that when elements on the periodic table are arranged according to increase in atomic number, there is a recurring pattern. There is a repeating chemical reactivity. Let's look at the color coding here. If you look at, say this is 1, 2, 3, 4, 5, 6, 7, all the way to 20, there is the color coding tells you that there is a recurring pattern. Look at the purple, there's a purple again, there's a purple again, it's coming back again. If you look at lithium and then sodium and then potassium, these are group 1 if you the periodic table. So the reactivity, the recurring pattern on chemical reactivity, all right, the recurring pattern is what we call periodicity. When you look at the chemical properties of element, you will notice a repeating pattern. We call this periodicity. These are the main group element. You may wonder why we don't look at B or we don't say 1A and 1B. No, B, their chemical reactivities are unpredictable. We cannot predict, but for main group, 1 all the way to 6A, can do that. This on table 2.3 on the periodic table, this name, special name for group 1, there is a special name for group 2A, there's a special name for group 6A, special name for group 7A and 8A, which you should know. Alkali metals are group 1, and these are the elements. You don't need to memorize that. Oh, I need to know this is lithium. I need to know what I'll give you the what? The periodic table. I may ask you which one of the following is an alkali metal, but if you don't know an alkali or alkali metals are group 1, and then you will miss the point. So I may use the terms you see here instead of the numbers. On the periodic table, you will have the numbers, of course. You may not see 1A, 2A, or so forth, but reconcile the special name. 8A noble gases, they don't react. Halogens are group 7. Halogen from the Latin salt forming element, there is halogen. These are group 6A. So remember what constitute, and they all react the same way. Those are special names for special group, and there are only 5 of them you should memorize. You should know what constitute. Any question on the periods, groups? So far so good. Let's move on. If you look at the color coding here, you may not have this color coding in the exam. You may not have these names right here, you see here, all right? But let me just expand this so that you can see. I'm just gonna expand this so that we see. If you look at the color coding here, it breaks down the periodic table into 3 parts. We have the metals, we have the metalloids or semi-metals, and non-metals on the right top corner of the periodic table. Except for hydrogen, anything on the left side of this zigzag, this is staircase, you will never miss this bold zigzag line on any periodic table. It separates what? Metals from non-metals on this side of the periodic table, except for what? Hydrogen, anything on this side, on the left side of this zigzag, metals. On this side, they are non-metals. You should know how to, all right? Suppose I give you in the exam black and white periodic table, there is no color coding. How will you know which one is which? It's very easy to, to remember that hydrogen is a non-metal. But here is what you need to pay attention, and how will you identify. This is what I recommend. Starting from poron, we call this poron. You code diagonal poron goes to silicon, code down, that is germanium. No, yes. Then arsenic, antimony, and tellurium. Some others consider polonium and astantine, number 85, as metalloid. But since this is the only element, how many of them? 1, 2, 3, 4, 5, 6. These are semi-metals or metalloids. What that means, elements which goes in between what? Between metals and non-metals. So I'm just gonna, this is what I usually see my students when I used to teach face-to-face, and I give them black and white periodic table. I see somebody shading this. They shade real quick, like, oh, let me shade this, let me shade this, let me shade this, let me shade this. That way you will separate metals and non-metals. All right. So on the left side of the periodic table, when you say left, even neon and fluorine is on the left. So how will you know? It is based on this zigzag line. Understand what left with reference to what? With reference to this bold zigzag, and I pointed out what constitute metalloids. The rest are metals. You may not know the chemical name of number 104, but from what I just went through, you should be able to classify as a metal. You may know what this means, you may not know what this means, but you know for sure this is a metal, this is a metal, this is a metal, this is a metal. You know, anything right here is a metal. Remember, these guys, they are in there. So metals are on the left side of the periodic table. Let me minimize this just in case someone asks a question, I don't miss it. So here are the metals, non-metals, and hydrogen is the only one on the left side of the periodic table. You should know the properties of metals. They are shiny, that is last shiny, that means it's shiny. You cannot miss a metal. If I have a metal and a piece of plastic, you can tell that this is a metal. They conduct heat and electricity, all right? And they are solid except mercury. Mercury is number 80 right here. Most are solid at room temperature. At room temperature. If you look at the properties here, these are for the metal. The opposite of this is or are properties of non-metals. Non-metals. They do not conduct electricity, all right? They are gases, predominantly they are gases except for liquid bromine and solid iodine. Most of them are gases at room temperature. They are gases at room temperature. Metalloids, these are metalloids. The pink colored, I'll walk you through on how to identify the metalloids. There are those properties goes between those of metals and non-metals. Their properties goes in between those of metals and non-metals. So if I were you, I'll just be able to go back to non-metals. All right, thank you, Anthony. Let me go back to metalloids or non-metals. Non-metals are on non-metals are the green one you see here. All right, they are on the right side of the periodic table, except for hydrogen here. Except for hydrogen, mostly they are gases except bromine. This is liquid at room temperature, and iodine number 53 is solid at room temperature. The rest, most of these, they are noble gases. Chlorine gas, oxygen gas, nitrogen gas, most of them, they are what? They are gas at room temperature. In case you want to know the properties of non-metals, it is the opposite. They are dull in appearance. They are dull. They are not what? They are not lustrous. They are not shiny. Non-metals, they are poor conductors of heat and electricity. A piece of wood will not conduct electricity. If I try to complete the electric circuit with a piece of plastic, it will not, the light might not light, right? So it's all that's what you need to know as far as metalloids are concerned. So I hope I answer your question, Anthony. That's what you need to know as far as non-metals are concerned. You should know what they are. Metalloids, you should know what constitute those as well. You should know what constitutes those as well. Now, any question on 2.5? Please read again. Use index card to memorize until you commit to your memory. Special name for those special group. What is a group? What is a period? What's a series? Properties of metals, properties of non-metals. All right. Is there a study guide for the quiz? Said no study guide for the quiz. You have to study those sections, chapter 1. But for exam, I'll give you the study guide, but not for the quiz. 25 questions. Let's move on to 2.6, chemical formulas. All right. Compounds are represented by chemical formulas which indicates the number of atoms in a compound. For example, here is the chemical formula for H2O, all right? This is the chemical formula for H2O. The subscript indicate the elements, like we have two hydrogens, all right? These are two hydrogens, you know what it means, and one oxygen in a molecule, all right? When we talk about molecule, all right, here molecule, it refers to non-metal molecule. You know, there's some vocabulary you should build as we go along. And then for formula unit. Molecule is two or more non-metals bonded together. So when we say a molecule here, this is a molecule, this is a molecule, all right? This is a molecule because they are it constitute non-metals. Remember, we just talked about what constitute a metal, what constitute a non-metal. So if a compound is made up of two or more non-metals, that is a molecule. A formula unit here, there is an R at the end. A formula unit refers to ionic. We're gonna talk about ionic compound, which is metal plus non-metal together. They must be a metal, such as NaCl. So we'll see how to represent those when we say a molecule, molecular compound. So coming back to that, a molecular compound, I can say that is always has non-metals. Molecule, formula units, all right? For non-metals, we say molecule. For ionic compound, we talk about formula unit. Here are just few examples of molecules. If you look at the elements in the chemical formulas for all these, they are non-metals. They are non-metals. Thank you, Natalie. Sometimes some folks get disconnected. I'm just gonna let you in. All right, if you look at this right here, we're gonna talk about in chapter 8, chemists use color coding, just to give you when you read, chemists use color coding to represent atoms of element on the periodic table. Hydrogen is always white, oxygen is always red, plug is always carbon, chlorine is always green, and whatever. So when you see that, there's a pattern in representing molecules and atoms of element on the periodic table. Di means two. There are 7 diatomic molecules, all right? There are 7 diatomic molecules on the periodic table. What does diatomic? This is hydrogen gas. This is nitrogen gas. This is oxygen gas. This is fluorine gas. This is chlorine gas. And then this is bromine liquid. This is liquid. And this is solid iodine. These are diatomic in nature. Diatomic means exists as 2. So wherever you see gas, these are gases. We're gonna talk about later on. These are gases, so they exist as gases. Oxygen gas, nitrogen gas, fluorine gas or chlorine gas, not chlorine atom. H alone is hydrogen atom. So know what constitute the atomic molecules. Let's see types of formulas. We have empirical formula and molecular formula. We're not going to calculate. Some of you may remember from introduction to chemistry, or if you are taking this course, you may have been asked to calculate empirical formula. At this time, we are not calculating, but by chance looking at the number of atoms and in a compound. Empirical formula gives the lowest odd number. You see this? Lowest odd number of ratio of atom in a compound. I can have benzene. This is benzene, 6H6. This is not empirical formula. Empirical formula will be CH, because I'll divide this by 6, I'll divide that by 6, and that is what I have. I can have here, I can have this dinitrogen tetroxide or this is not empirical formula because I can still divide by 2 everywhere, and this is what I have for this. This is the empirical formula, nitrogen dioxide. So empirical formula, it's got to be in the wholest number. This is empirical formula because I cannot simplify anymore, any further. This is the empirical formula, carbon monoxide, all right? Whereas molecular formula indicate the exact number of atoms, all right? Exact number of atoms. Let's see, if given an example as this, give the empirical formula for decapiene, whose molecular formula. So all what you need to do for this example is divide everywhere. If I divide by 2, this is going to be 5, and then 7. I cannot, use fraction. It must be a whole number. And this is the empirical formula for this compound. So in the exam, I'll ask you which one of the following is an empirical formula of, then some of them, or maybe 4 of them will not be empirical formula. Or given a compound like this, I may say, which one of the following is an empirical formula for this compound, and multiple choice A, B, C. All you have to do is simplify until you cannot divide it any further down. That is the empirical formula for a compound. You'll see every this. What was the example of molecular formula? All right. Example of molecular formula, it gives you, let me back up to what molecular formula. Molecular formula is, all right, molecular formula gives exact number of atoms of each element in a compound. For example, here is, if this is the empirical formula for this compound, what I have on my whiteboard here is the empirical formula for this molecular formula. It gives you the actual number, all right? You will see that, it's not simplified. That's how I'll phrase it, or how I'll look at it, molecular formula. So you'll be given actual number of atoms in a compound. You'll be given actual number of atoms in a compound for that. So we will look at this in details in chapter 8, how to look at the representation of the molecule. It's going to be relevant in organic chemistry, that when using two-dimensional to represent three-dimensional structure of, of a molecule, the bold wedge means it is taking off the paper, like it's pointing towards you, and the one in a dash wedge means it's going back, and the solid line means it is in plane. Just to interpret that, I may not ask you that. To do that, we will not look at in details. We will not look at in details the pictorial representation. I'll leave that until chapter 8, when we look at the valence shell electron pair repulsion models and the chemical bonding. I'm gonna come back to that. Now, so in that section, all I want you to remember is differentiate between molecular formula and empirical formula. It's not fancy. I'm not gonna ask you that, determine the molecular formula. I'm gonna come back to that in details later on. Let's see. Ionic compounds and ions. At the outset, compounds, all right, compounds right here, compounds, I want to draw a flow chart for compounds that it can either be, all right, it can either be ionic compounds, all right. It can either be molecular compounds, which we will look at. Remember, molecular compound are compounds made up of two nonmetals, two or more nonmetals. These are compounds. And then we can also have acids right here, an acid. All right. Ionic compounds can either be binary, that means it's got two, that is metal plus non-metal. For two elements, sodium chloride is an example of, I lost my whiteboard. I lost my whiteboard. Yeah, there we go. Yeah, I was just drawing this flowchart right here to show you classification of compounds. When you see ions and ionic compounds, compounds can either be ionic compounds or molecular compounds. And these are non-metal plus non-metal. Acids, we're gonna see this later on. Acids, we're gonna come back to this. It's just molecular compound in aqueous form. Ions, the first term right there, I think I defined that earlier on at the beginning of chapter 2. Ions could be, these are charged, we call these charged particles. It can either be positive or negative, positive or negative. It can be anion, it can be cation, or it can be polyatomic ion. This is negatively charged particles, such as fluoride, such as chloride, such as O2. All right. Cations are positively charged, and it could be Na positive, it could be Ca2 positive, it could be Al3 positive. This is 3 right here, 3 positive. And polyatomic ion here, these are groups of, let me go here and define what polyatomic ions, group of atoms with an overall what? Charge. That means it's a collection of atoms. For example, CO3 with an overall charge of -2, SO3 with an overall charge of -2. I can have PO 4 with an overall charge of -3. These are a group of atoms with an overall charge. Let's back up to monoatomic or positive and negative, positive and negative. You may have seen me writing negative, positive. How do I know? It's by using the periodic table to predict the ionic charges. Metals tend to lose their, valence electron. I know we haven't talked about the valence electron, but you can use the periodic table that all group 1 will form +1. All group 2 will form +2, except for beryllium right here. Except in group 3, not all group 3 though. Most, all right, most or common metals which form +3 is aluminum. Boron will not. It is a metalloid and it will not lose any of its valence electron. When you get to non-metal, all right, for non-metal to predict the ionic charge, okay, predicting ionic charge for monoatomic ion, all right, group number, all right, group number tells you what is the charge for that. You have to teach yourself how to keep track of this. Group number. For non-metals, all right, non-metals, ionic charge is given by group number -8. Group number -8. For example, nitrogen will be 5. It is in group 5 -8, which is -3. So that's the group number, or how this -3 is written. And it is not written like this. I don't want you to think that it is written like N and then 3 like that. There's a way it is written as a superscript and then negative like that. That's how you write the ionic charge. If you look at 6 oxygen, all group 6 will be 6 -8 is equals to -2. That's why all these we have -2, -2. In case you are wondering, you don't have to fry your brain trying to memorize that. Oh, I need to know this is plus. It's just a concept of saying that. Oh, this is group 1. They'll form +1. This is group 2. Except for what you are given there, +2, 3. But when I get to non-metals, this is what you need to use. Ionic charge is given by group number -8. Watch this. If I have been 7, maybe fluorine, for example, it will be 7 -8, and this will be -1. So all of them, all group 7 will have -1. Well, you may see hydrogen and being here and here. Hydrogen is special on the periodic table because in some reaction, it reacts like a metal by losing an electron. In the other reaction, the same element can gain an electron. That's why it's on both sides of this classification. You may see, so you may have noticed that in some periodic table, hydrogen is placed just metal right here because it doesn't belong anywhere. It can be a metal, it can be a non-metal as well. No, not non-metal, but react like a metal. I know previously I say it's a non-metal. But in this case, even though it is a non-metal, it reacts like a metal by losing an electron to form positive. It can gain an electron to be like helium. That is why we have a negative on this side. That's how you use the periodic table. Now, noble gases, they don't gain, they don't lose, so you cannot use that. That's how you predict the ionic charges for cations and anions. Cations are formed when at least one electron is lost, forming monoatomic. That means it is 1. This term mono, in reference to what I said here, poly. You see this? Poly. Mono is 1, but here we are many. So anions, negatively charged, when an electron is gained. Remember, electrons are positively, negatively charged. So if one electron is gained, or 3 electrons are gained, and then you'll have an overall charge of negative, means 3 electrons are being gained, means 2 electrons are being gained when you have like that for cations and anion. This is the fundamental concept you need to understand in order to master writing the correct chemical formulas for ionic compounds. Because if you don't know the ionic charges, you will not know how to write the chemical formula for ionic compounds. So that is where we are going. That's where we are going. Oh, well, here are a few examples of cations which are positively charged. You may see this and you wonder, why is this one? Where is it on the periodic table? It falls under polyatomic ions. There is a table for comprehensive for polyatomic ions, all right? And I want you on them. Let me just pull even that. Now that we are on here for polyatomic ions, let me see if I can go to, is that, no. Chapter 2, polyatomic ion versus cation, which I want you, don't you know, I want you to go and practice, use index card until you memorize common polyatomic ions. I have polyatomic ions, a lot of them right here. Polyatomic ion, common polyatomic ion from different others. You know, you can have this and then click this. If you see that, you can click that and it will load. You see, these are common polyatomic ions with their names. So group of atoms with an overall charge. I think I do have another set right here. Let's see what is in here for polyatomic ion. Still the same thing, you know, these are common. Do I need to memorize? Use the one in the text so that you know what they are. I was just giving you an array of polyatomic ion, so that you know what constitute the polyatomic ion. Please read on that, and you should be able to, until you master the common polyatomic ion. Ammonium is one of the polyatomic ion. This is a transition metals with copper one. You also need to learn those with more than one, charge. Learn those with more than one charge. Can polyatomic ion have a positive or negative charge? Jennifer? It can go both ways. Let me give you, there are few polyatomic ion with an overall charge of positive, all right? There's a few, like for example, here is ammonium. We have hydronium ion. This is a polyatomic ion. These are the common one you will see with an overall charge of positive. Jennifer, can polyatomic ion positive or negative? Yes, it can go both ways, but majority are negatively charged based on that example I gave you. Based on that example I gave you, most polyatomic ion are anions. That means they are negatively charged. Well, let me say something about the Roman numeral. Roman numeral, and you need to, I don't know if you got to pay attention to. Element on the transition or transition elements, not all of them, transition metals here, they can lose one or more electron to become positively charged. And there is no formula except you have to memorize. For example, Cu, positive one, Cu, 2 positive. There is iron, 2 positive right there. And there is iron, 3 positive right here. As far as polyatomic ions, no, monoatomic ion, which form more than one charge, such as this, we use Roman numeral to name them. We say this is copper what? Copper 1 ion. This is copper what? This is copper 2 ion, Roman numeral, and this is iron 2 ion, and this is iron 3 ion 3 ion. We use Roman numeral when you're dealing when an element is on the transition, and not all of them. You got to know the the what Roman numeral it means, or it indicates the charge on. If you look at this right here, it means 1. If you look at this, it means 2. If you look at this is 2 right here, here, and here. If I were you, I will look at in the text what common ions which form more than 1. There is a term here, you may see this, cuprous. The Latin name, it's an old way. I can say this is called stock system. We call this stock system of naming. It's the modern way of naming cations monoatomic with more than one charge. Roman numeral indicating the charge on the cation. The old way uses OUS and say old way, old system or method. We call it method. The one with the greater charge ends with what? IC, whatever you're naming that. Less charge ends with OUS. Cupric. So this is, they will call this Cu positive, this U Q plus. And then Cu plus, this is cupric. Right, so it's 1p. So cupric, this is 1p, cupric, cuprous, cupric, cuprous. You see that? The one with charge. Ferrous, ferric is an old way of naming those ions. So if you look at this, iron 2, ferrous, copper 2, cupric, all right, iron 3, ferric. If I were you, I will look at the transition metals and write next to each other. If you look at what I did, this is copper, and if you on the previous slide we had copper 1. That's how I'll differentiate between the two. If you look at the example right here on the slide, I put the ion together. It will not, I will not miss it. That's how we, over time, you know, I've seen that if you synthesize right now on this table, right, it doesn't really help you. You know, you look at it and you're like, okay, this is too much information. Well, you don't need to know the old method. You don't need the old method, David. I'll try to stay away from the old method. You know, you will never see, even when you go to the lab, no one will say, oh, take ferrous and then do this, or cupric. And no, we just only say copper 1, copper 2, mercury 1, mercury 2. All right. So, you know, why learn the old way? Yet, you know, we have gone past that. So learn the modern, the stock system, and you have explained to you where the Roman numeral, it has to do with those elements in the inner transition metals. Here are anions are negatively charged, and these are the common ones. So what I'll do is, if you look at the links I posted on Canvas, it's coming from anywhere, but I just wanted you to be well-rounded. I'll stick with what we have in the text because that's where the question will come from. So no, come on. Monoatomic anions. The other is mixing polyatomic ion with monoatomic ion, but these are monoatomic ions, and there is a pattern. All right, there is a pattern here on naming polyatomic ion. For monoatomic, for anion, let's see monoatomic first. Monoatomic anions. That means they are negatively charged. And if you look at the naming, it ends with IDE. We change the N to IDE. For example, here from the word hydrogen, it is hydride. From the word fluorine, it is fluoride, chlorine, chloride, bromine, bromide. You know, there's a systematic way of naming that. This is a polyatomic ion. Gonna look at that. Hydroxide, oxide, oxygen. I wanted you to see how we name the monoatomic. When it comes to, all right, when it comes to poly, all right, excuse me. Getting my pen. When it comes to polyatomic ion, all right, polyatomic ions, that means more than one. There is a pattern here. You have to, when you write, when you make your own notes, and I recommend again use index card. You have to look at the number of oxygens. Mostly they are oxyanions. Mostly they are we call this oxyanion. That means they have oxygen in it. They have oxygen in it. The number of oxygen determine how you name them. How you name them. The number of oxygen determine how you name them. I'm gonna give you example, and you should be able to write the chemical formula with an overall charge. If you look at this, there's a way to name that. You may see on this PowerPoint slide, but suppose you are not there. I can have this. This is another example. All right. I can have another example here. PO3, PO4. If you look at how I've been naming this, there is a pattern to start off with. This one right here, we call this nitrite. We call this nitrate. We call this sulfite, ITE. We call this sulfate, ATE, sulfate. This is sulfate, ATE. In this series here, there is a pattern. The one with less number of oxygen ends with ITE. The one with greater number of oxygen ends with ATE in a series. It does not mean necessarily 3 oxygen or 3 oxygens or 2 oxygen. No, it does nothing. In that series, which one has the greatest number of oxygen? If it is right here, nitrate, and then there is nitrite. If you look at this sulfate, there is sulfur, and then sulfur, oxygen, oxygen. The one with less number of oxygen ends with ATE, ITE, and so forth. So if I look at this right here, if I compare sulfate, ATE, and sulfite, all right, it ends with ATE, the one with great number of oxygen, and with ATEs. There's not all of them have 2 series. Some of them they are standalone. Some of them they have more than that. Common one. What I've just given you are common ones. This one is by itself, doesn't have two, so you need to know. Carbonate, this is a common one you will see. Acetate ion, you see here, these are common one. Chromate and dichromate, these are common polyatomic ion. So here are just few examples. I've just given you on my whiteboard examples of polyatomic ions. Polyatomic cations, ammonium, there is hydronium. Somebody had asked, I think it was Jennifer, about polyatomic. Here is an example, ammonium, and you should know, not ammonia, ammonium. Ammonia is an H3. Sulfate, and you know now sulfate because it has 4 oxygen. Because in the exam, you may say 3 oxygen and somebody will confuse with sulfite, sulfate. I've given you a hint on. So at this point, before we look at the ionic compound, what I was just giving you is how to predict the ionic charge using the periodic table, how to name monoatomic anion, how to name monoatomic cation, and so forth. Please learn that. As far as compounds are concerned, all right, as far as compounds are concerned, 2 things you can be asked. Either you are given what? The name, and you are asked to write the chemical formula, or given the chemical formula, you are asked to write the name. It cannot get complicated further than that. As far as the compound are concerned, you can be asked to write the chemical formula given the name, or given the name, all right? Given the name, you should write the chemical formula, and vice versa. We will start with ionic compounds. Remember, there are 3 types of, my flow chart. Remember my flow chart? Ionic compounds, all right? And there is molecular compounds. Ionic compounds, they have here ionic compound. Metal plus non-metal. That's how you can identify this is an ionic compound. All right, using a metal, and an electron is transferred. So if this is transferred from, for example, sodium, we lose an electron to chlorine to form sodium chloride. You know this is positive, and this is negative. There is a strong attraction between that. That's how the ionic. Let me show you, all right, how a general formula, all empirical formulas are written. How do I know that? Empirical formulas. Remember empirical formulas? The simplest. I'll show you how to write the correct formula. We use what we call crossover rule. All right, this is a method of writing the correct formula for ionic compound. If you can predict the ionic charge from what we looked previously, you bring down the numbers, not the charges. I don't want you to bring down it's the number, like this is -1, this is +1. If it is 1, we do not show that. We do not show that this is N1, and it is coming from chlorine, by the way, all right? And Cl coming from sodium. You don't, when you cross, from the word cross, you bring down, and you end up with the correct formula for sodium chloride, but we don't include this. It's just the way it is, like that. Na is based on the formula. Suppose I have something like Na with +1 and 2 like that. The crossover rule tells me that the correct formula for that is N2 from oxygen, and 1 is coming from sodium. You don't see 1 indicated in there. You don't see 1 indicated in there. So that is what I want you to know as far as crossover rule is concerned. If you can switch it, that's fine. Where is the empirical formula coming in? Let me show you where the empirical formula is. If it is lead, all right, If it is, this is PP4, there is 4 positive, and then there is PP2 positive. This is lead 4 ion, and this is lead 2 ion, lead 2 ion. If it reacts with oxygen, the first one, if it is PP4 positive and oxygen in there, this will be PP2 from oxygen and 4 from lead. This is where the empirical formula comes in, that you need to divide by 2 across so that this and that will go, and the correct formula is PPO2. This is the empirical formula. You have to simplify, all right? You have to simplify if need be. You have to simplify if need be. Well, sometimes you may be required to use parentheses. For example, if it is calcium ion, all right, this is calcium, not calcium 2, but calcium ion. And say, let's say it is reacting with hydroxide. You gotta know the name, hydroxide, like that. If I was to write that, somebody might think that, okay, I'm just gonna write Ca and then OH and then put 2 like that. No. You have to use parentheses wherever you are handling polyatomic ion. It is a group of atoms which react as if it is one. So for this is what we will do for this. You have to use what? Use parentheses. So next time you see a parentheses outside, know that it is a polyatomic ion being involved. It could be ammonium carbonate, all right? NH4, let me show you 4. This is ammonium ion, and then let's say it's reacting with carbonate like that. This is carbonate. So this will be NH4. Use parentheses. This 2 is coming from carbonate, and then you just leave alone that by itself. Leave alone that by itself for ammonium carbonate. Kenneth, can you go back? Let me go back on my slide right there. Is that what it is? Is that? All right, yes, I was talking about whenever you are handling polyatomic ion, that means an element or a group of atoms. This is polyatomic ion. You see this polyatomic ion right here? Likewise to other polyatomic ion, you use parentheses. Don't just write it and say Ca and then OH and then say 2. No, what this means, you have only 2 hydrogens. But this one is 2 hydrogen and 2 oxygens. That's what I meant when to use that, all right? So be careful whatever you are dealing with. I went ahead and show you another example on how to handle polyatomic ions. The crossover rule. You see these 2 right here? These 2 and positive 1 right there? It is right here what I was talking about, the crossover rule. Once you master that, you will nail down the writing of polyatomic ions, or I mean polyatomic, no, not polyatomic, but ionic compounds involving either monoatomic or, monoatomic ions or polyatomic ions. So, and remember to cancel that. This is the crossover rule. It didn't explain to you, but you know what is going on here now. When you see an arrow coming this way and this way, what is happening is crossover rule. We do not bring the charges. Don't say it is positive 3 and no. I saw one student, it's not, a couple of semesters ago, what they did, the student, this is what the student did. Maybe they didn't pay attention in my lecture and they say, all right, this is the chemical formula for magnesium nitride. It looks fancy, like, more of the same as like what he was talking in the lecture. You see the mistake they made, like, I think you got to bring down. It's not that bringing down. You have to cross over the charges and you'll end up with the right the right formula. And remember to simplify the subscript once you cross over. This is wrong right here. Simplify once you get. I gave you an example on how you simplify. Here was an example. You know, when you cross over 4 and 2, you end up with 2 here, and then you end up with 2 here, right here, and you simplify that. That's what is meant by lowest whole number. Divide by the greatest common divisor, GCD. All right, GCD. That's how to write the correct formula for. Correct formula for ionic. Remember, the key thing is what? Crossover. Don't forget what I just said. That as far as compounds are concerned, either you are told to name, given the formula, or given the formula, write the chemical name. And in chemistry, nomenclature is just naming. Don't get this term right here scare you. That is, what is the nomenclature? Nomenclature is the naming. What is the systematic way of naming compounds? We have looked at how to write the formula for ionic compounds. How do we name them? All right, we will look at how to name ionic compounds, how to name the acids, how to name the binary molecular. And when you see binary, that means 2, and then there is the simple organic compounds, organic compounds. All right, inorganic compounds, these are compounds which inorganic compounds are compounds which do not have element carbon and hydrogen, and there is a systematic way of naming them. Those IDE, I explained earlier on, an anion and cation. If an anion is an element, change the ending IDE. Simply write the name of polyatomic ion. Write the name of a cation. If the cation have more than one possible, you know, write the ending. This is just how to name the polyatomic ion. We'll see in specific how to change the ending. I explained this one earlier on. How do we use, when do we use ITE, when do we use ATE when writing oxyanions? Remember, oxyanions means, here, oxyanions. This means polyatomic anions with oxygen. They have oxygen in their chemical formulas, oxygen. That's basically what that means, oxyanions. You have to look at the series. If I look at this, the one with less number of oxygen, it ends with ITE. The greater one ends with ATE, sulfide, sulfate. I talked about this earlier on. Make your own notes on how to use ATE. The easiest way is having 2 of them on one index card: nitrate, nitrate, nitrite, nitrate, sulfate, sulfide, and over time you will be able to differentiate between the 2. Phosphate and phosphide ion, maximum of 4 oxygen. If you look at what is being focused here is the number of oxygen, It increases, and it's just gonna give you how to name oxyanion. I have about 3 links on periodic on the module 2, on chapter 2, on how to write the correct formulas for polyatomic ions and monoatomic ions. All you have to do is teaching yourself, memorizing, how do I end up with this? All right, how do I end up with that? That's how to name more polyatomic ions, how to write the correct formula for monoatomic. Now, for molecular compounds, all right, molecular compounds. These are made up of non-metal plus non-metal. Non-metal plus non-metal. How do I know that? It's just by looking, you know, at this point, it is expected that you are proficient in breaking down the periodic table into into three. You know where the non-metals, non-metals on the right, top right corner, metals on the left side, and then there are metalloids. Elements or compounds made up of two or more non-metals constitute what we call binary, and they have two. You need to remember the prefixes associated with this. You need to learn this. Prefixes are used to indicate the number of atoms in the compound. For example, here, CO, this is carbon monoxide. Mono means one, you have one oxygen. Two here, this is carbon what? Carbon dioxide. Carbon di for two, carbon dioxide means two. The point here is mono and di. If you look at this mono and di, for non-metals, two or more non-metals for binary molecular here, these are the prefixes you need to remember. Mono means one, di means two, tri means three, tetra means four, penta means five, pentagon, all right. Hexagonal, hexa means six, hepta means seven, heptalon event means seven, octa, octave, that means eight, octobus, maybe just eight tentacles, nona means nine, and deca, we have more than that, which we are not going to get into details. All right, these are the prefixes which are used to indicate the number of atoms. There is no crossover here, please. There is no crossover. So if I have a compound such as this, all right, such as this right here, look, two, like that. I can have something like that. This is nitrogen dioxide. This one is dinitrogen tetra oxide. Sometimes they say tetroxide is the same thing. You got to make sure you know. Tetroxide, and then this one is dinitrogen pentoxide. Dinitrogen pentoxide for 5. Dinitrogen pentoxide for 5. That means you have five. Oxygen. Take note of mono. We don't use mono for the first element. You can imagine this right here. You can imagine right here. You can say monocarbon monoxide. We don't say monocarbon monoxide. No, we don't say monocarbon then dioxide. We don't use mono for the first element. We also look for the second element when there is more than one series. More than one series, we say mono. All right, we say mono for the second one. So as far as molecular compound, all I have to worry is the prefixes here. You need to commit to your memory. It indicates or denote the number of atoms in each element in the compound. Look here, carbon dioxide, carbon tetrachloride. We don't say monocarbon tetroxide. Tetra means 4. This is dinitrogen, all right? Pentoxide, not pentaoxide. We remove A, all right? Carbon monoxide for 1. And that is how you got to pay attention is the prefixes you have here. You can practice more on end of chapter, even on the homework. This is what you need to remember as far as binary molecular compounds, binary molecular compounds. Now, in my flowchart, I had mentioned earlier on about acids. Let me say acids. Before we look at section 2.9, let's look at the acids on my whiteboard right here. I can say here there are two types of acids. All right, we have binary acids and ternary oxy acid. That means they have oxygen in their chemical formula. Let's see binary acids right here. That means it got two elements. In binary acid, they must have hydrogen. They must have non-metal. It must be aqueous. It must be aqueous. Example is HF, aqueous. You have to indicate aqueous. How you name this is hydrofluoric acid. Hydrofluoric acid. HI, this is hydro, and there is aqueous right here. Hydro what? This is hydro. Iodic acid. Hydroiodic acid. All right, hydroiodic acid. HPR. All right, HPR aqueous. This is hydroiodic acids. All right, Jennifer, can you go back to the slide before this one, please? Is it on my notes right here or lecture? Jennifer, is that what you're talking about? Or notes? Right, is that what it is? Let me go back one. Notes, yes. What is the question right here? What I'm talking about here is for binary acids. For binary, binary means two. They must have hydrogen in the chemical formula. They must have non-metal. Maybe I didn't put right here. Non-metal in the chemical formula, and must be aqueous. These are the three signatures I'll be looking for binary acid. And if you look at this is an example. There's an hydrogen in the chemical formula, there is a non-metal, and it has a physical state of aqueous. Those are the three things I'll be looking for in binary acid. And I gave you, or if you are paying attention, the word hydro, it is used wherever you are handling binary acids. Hydroiodic. This is bromic, sorry. I should have said bromic, not iodic. It cannot be that. This is hydrobromic acid. That's how you know you're dealing with acid. And then, these are just, even this one, this is the one you will see in the lab. HCl, everybody knows HCl and must be aqueous. By the way, chemists are very specific. You should be able to state the, the physical state. Anthony, do acid always end with ICE? Not necessarily, but for binary acid, it ends with ICE. But when we get to oxy acid, it will change. And I'm going to show you in a moment. I'm going to show you, Anthony, in a moment. Your question is no. Do acid always end with ICE? For binary, yes. But when we get to oxy acid, which I'm going to show you in a moment, it will not always end with ICE. So let's see. This one is hydrochloric acid. You'll see this, or maybe you are working, you will work with it in the lab. Now, these are just examples of binary acid. But now, to answer your question, Anthony, oxyacids. How will I identify an oxyacid? All right, how will I identify oxyacid? Oxyacids have one, these are the key signatures. They must have oxygen in their chemical formula. They must have hydrogen in their chemical formula. All right. They must have non-metal, all right, non-metal in their chemical formula. And it must be aqueous, all right? It must be aqueous. That means dissolved in H2O. It is self-explanatory when you look at oxy for oxygen. Oxy for oxygen. For example, here, H2, SO3, and then aqueous. And then this one, H2, SO4, and then aqueous. When I have this, I know I'm dealing with an acid. In order to name these acids, all right, in order to name these acids, it will call for bringing in the knowledge of naming polyatomic ion. If I look at this polyatomic ion, let's see, I'm gonna draw here so that you see polyatomic ion. The polyatomic ion here, polyatomic ion involved, there is SO3 to negative, there is SO4 to negative. This one is sulfate, and this one is sulfite, I-T-E, sulfite. This one is sulfate. The one with I-T-E, when naming the acid, ends with O-U-S. The one with A-T-E, when naming acid, ends with I-C-E. So this is what I'll do for this H2 SO4. Let's start with 3 first. This is sulfurous acid. OUS, sulfurous acid. This is sulfurous acid. Whereas H2, SO4, and by the way, this is aqueous. I forget to put this aqueous. This will be, we got 6 minutes. This will be sulfuric acid, sulfuric acid. So Anthony, if you look at how I'm naming now and oxy acids, it does not end with ICE. The one whose polyatomic ion ends with ITE chain to OUS. The polyatomic ion involved in the acid ends with ATE, it changes to IC. Let me go back again. The polyatomic ion ends with ITE, naming of the acid ends with OUS. So, having said that, you know what this means. 3 and H3O, this one is HNO2. This one has nitrate, this one has nitrite. So this is nitric acid, and this one is nitrate, nitrous, OUS, nitrous acid. So polyatomic ion affect how we name the oxy acid. The OUS and ICE, we don't say hydronitric acid or hydronitrous acid or hydrosulfuric acid. You see here, it is not hydrosulfuric acid. Hydro is for binary acid, or binary acid. So pay attention to polyatomic ions for oxy acid when naming them and writing their chemical formulas, real quick, to wrap up chapter 2, let's see, so simple organic compounds. Yeah, it's just to mention, to give you a head start on what organic compounds are. To this point, the compounds we have been looking at inorganic compounds. Inorganic compounds, except for carbonate ion and cyanide polyatomic ion, most of the compounds we have been looking at do not have element carbon. Compounds which contains, compounds which contain element carbon fall under the organic compounds. And there is a broad chemistry on compounds containing element carbon. We call organic chemistry study of carbon containing element. It is the only, you may wonder why only carbon on the periodic table. It is the only element on the periodic table capable of self-linking, like to form a long chain similar to this. That's why we say organic got only carbon was itself. There is quite a number of, you will see in details in if you're to take organic compounds down the line. I don't want to go in details into the functional group. It's just to mention what it is. There will be a time will come where you will take organic chemistry in details. But just to give you a head start, there is a branch of chemistry which deals with only compounds which contain element carbon. And with that, I just want to end there today, our lecture. Please make sure you complete the online homework assignment before the due date. I have the online homework due date. Please use the study module as well. What I may do is, for those who are ahead of the game, maybe you are done with the chapter 1 homework assignment, you are done with chapter 2 homework assignment, you are done with chapter 3 homework assignment, and you want some practice for those chapters. I will reassign those chapters, but you will see it is practice. It will just be like practice. I may just label that as practice. It will not affect anything on your grade book. Just you want some remedial work. Even on dynamic study module, you will see those also assign you as practice, so that you will have that. If there is no question, will stop sharing my screen right now before I end the lecture. I want to say thank you, everyone. I appreciate your time. I will post the lecture recording later on once I process. Peace safe. I'll see you next Tuesday. Thank you so much, everybody. Thank you, Drake. All right. Sure. Natalia Sanchez, Jonathan, thank you. Tina, Christine, thank you, everybody. I really appreciate it. Peace safe, Danielle, peace safe, everybody. Appreciate it. Class is ending now.